Hello there, and welcome to a short percent change video. I've had some folks request a little bit of help there. So the formula for percent change is the ending value, that's your final measurement in the experiment, minus your starting value. And then you divide that by your starting value. One thing I'm going to mention, I'll reiterate, it's really important to keep the sign as you work through this. So when you calculate that, then you multiply it simply by 100 to get percent. So the example I'm using here is from the Osmosis lab, and I'm just going to make up some really easy measurements for myself to work with. So I'm going to say that the measurement I took at the end was, I'm going to say 15 centimeters with my ruler, oh, not cm, centimeters, and that my starting value was 10 centimeters. So yours would be, oh, I just want to put cm in there. So yours would be a little bit different for that. Okay, so to set that up, I'm going to, and this would be, for this particular experiment, we're going to make this for our salt water. And let's go ahead while we're here and make a pure water. Oops, we're a little too far there with the tabs. Okay, so pure water. And I'm going to say for that particular experiment, I'm going to make the ending value, oh, let's make it 18 centimeters. That seems kind of big, but we'll use that one. And then we'll make our starting value 16 centimeters. Okay. So to do these calculations, you just simply plug these values into the formula. You do have a calculator enabled for you on quizzes that you can pull up. It's at the very top of the browser under lockdown. You can use that. Also, if you, I don't prefer that you use an external device because people can just plug the formulas in there. But if you hold up, you have like a real basic calculator, not a cell phone, because again, those can be programmed with percent change formulas. But if you have a basic calculator you just want to hold up that you're using that, that's okay too. Or you can use the one on the screen, that's just as easy. Okay, so to set up the first one, I'm going to go ahead and do the pure water. So I'm going to take, and I'm going to write now so that you can kind of see that a little bit better. I'm going to make some space here for myself. I'm going to use these values that I had up here, the pure water. And I'm going to switch to my writing option. Okay, so I'm going to take 18, which is my end value, minus my starting value. The formula is pretty straightforward, the main thing is that you can remember it. We do provide it for you on some exams, but make sure that you can memorize it for our quizzes. And then the starting value is 16. So usually the problem that people have is they can't remember what to divide by. I'd say even that's my problem sometimes, but I'll tell you a little trick to check and make sure you divide it by the right value at the end. So I can, if I want, bring a calculator in. So I've got one on my desktop. I'm just going to pull in and use. So 18 minus 16. And then simply divide that by 16. And then finally, and I'm going to get this weird small decimal, so that probably tells me something's off because it changed by a fair amount, 2 centimeters, which is a pretty sizable amount for something that started out pretty small. So now I'm going to multiply that by my 100. And that gets my final answer. Now, one thing I want to note here is the sign, and this is actually can really be your friend. So with percent, a lot of folks have always learned that you can't ever have a negative sign. In this instance, we don't have a negative answer here, but there are instances in the next example where you would get that, and that can be helpful. But keep in mind on the sign here, because the sign here is positive. So I'll tell you why that's important. Okay, so when you get to this part, then you would have your 12.5%. And I try to tell you, how many decimal places to use. If you ever put in an answer and you get it marked wrong because of the decimal place difference, just shoot me an email if you kept 2 places or 3 places. I don't want to ding you on that. So one of the things that's key here, though, is you keep, make sure you keep the percent sign and things like that. Now, you can write the word increase, but what I wanted to tell you here, whoops, let me go back to my inking. I think I jumped back out there. You can write the word increase, but the sign here will imply increase. So sometimes students forget which value to put first. So they basically end up that they can't remember whether to put the 18 first or the 16 first. So keep in mind what you want to do is just kind of use that kind of that logic approach. So when you went through the experiment, the ending value increased. So you started with only 16 centimeters, but you ended up with 18 centimeters. That should tell you that it's an increase. So you will have a positive sign. So at the end, if you get a negative sign, you don't have these values set up over here correctly. So it's really important that you think about whether it's going to be before you even start the equation. Did it go up? Is it an increase, or did it go down and it's a decrease? Because that's going to help kind of set a red flag for you if you get a negative answer and you knew it was an increase. And I use that for myself too, because sometimes I'm like, okay, which is it? Is it the starting or the ending? You know. Another way to remember that too is that, you know, sometimes I remember that ending has the letter E. It's earlier in the alphabet, and that goes first in the equation, and then starting goes last in the equation. And you're always dividing it by the starting value because that's your reference point. All right, so let's go down and try a same formula, but something different. So now we're going to use the saltwater experiment for part B. And so we have the ending value is, oh, and see, I can already see that I have a problem here in my data. So this is, again, you know, thinking about this experiment. And I know that this experiment tends to give you something smaller at the end. So I'm going to change my data. And this is, you know, I'm making this data up. You're going to measure and have a little bit different data. And let's pick something more odd there since I've got a calculator at hand. So my ending value is smaller than my starting value. So it decreased. So that should tell me I'm going to have a negative sign. And again, you don't have to always write the word increase or decrease. The sign already tells me that. But some students prefer to do that because it's just, you know, puts that whole idea together for them. Either way is fine because you're getting that information out there. Okay, so I just changed my data because I realized for saltwater, the whatever the potato slice that you're using should shrink. So let's go down here and enter that. So we have 7.5 and 10. Let me make a little more space for myself. And I'm going to go to my inking tool. And the inking tool just doesn't have the prettiest handwriting, so I apologize. So I'm going to have my ending value, which is 7.5 centimeters. That's what you've measured with your ruler. Minus, I believe I had the 10 centimeters. And I'm always dividing by that start because that's the reference point. So before you proceed through the equation, I can write my 100 here. Before you proceed through the equation, notice that you're subtracting a bigger number from a smaller number. That's going to give you a negative answer. Does that make sense? Did the experiment go down? Yes, it did. It was a decrease. So kind of backing up and thinking about that, I think will help you with the setup there. All right, so we're just going to bring my calculator in and probably get somewhat kind of similar answer because that's going to end up with a 2.5 there at the end. So 7.5 minus 10 divided by my starting point, which is 10. Okay, make sure you're hitting equals. Otherwise, you know, if you're a master with parentheses, that's fine too. Now I've got a negative sign there. Does that make sense? Did the experiment decrease over time? Yes, it did. Okay, so and then finally I want to convert that to percent. So I'm going to multiply it by 100. So let me get this out of the way. Go back to my inking here. I'm going to have a negative. Hold on. Seems to kind of want me to restart things there. Okay, so I'm going to have a negative 25%. Now, sometimes students get really bugged by a negative because they've been told probably numerous times in their life that you can't have a negative percent. And that's okay. So if you would rather report it this way, you can also say 25% decrease. Either way, whether you have the negative sign or the word decrease, you're communicating that same answer. Either way is fine. So you can write it that way too. Either way is fine. Because I know students have gotten that message a lot that they can't have a negative percent. So that's fine. And again, just think back, does that make sense? Did the experiment go down? So I can go back and look at my ending value here. Yep, it went down over time. So something similar that's here. So how does that tie into some things like the solution that goes on here? So hopefully you got your plant slice lost lost length over time. If you didn't, sometimes I have you run it a little longer, increase the salt concentration. So what you'd want to think about here is the water being pulled out of the cell. So this is the process of osmosis. So if you have, and everybody's experienced this on a physiological level, if you're in the ocean, you feel that kind of dried out feeling, or a really chlorinated pool, because those are strong ionic compounds that pull water out of your body. Also, if you're just drinking really salty drinks, let's say you got up and you had coffee and then you had soda a little bit later, or you had really salty food with that, maybe you had coffee and some really salty fast food, you feel that dehydration. The water is being pulled out of your cells. So what happens is when you eat something, and sugary foods do this too, caffeinated foods do this. We don't think about coffee, but everybody that drinks coffee, alcohol will do this. They've experienced that feeling of dehydration. So I'm not telling you anything new there, but it actually will pull the water out of your cells. So if you could measure your cells on a tissue basis or a cell by cell basis, they would have lost weight too. We use the plants because that's really easy to visualize and see that change that's there, and you can replicate that at home. Sometimes you get a situation where the plant slice in water shrinks a little bit. It's like, wait a minute. So if you're using true pure water, which is what we can use in a laboratory setting, but if you have really highly filtered or purified water at home, you should see that water moves into the cell because it's really low in solutes. But however, if you use tap water, which a lot of us are going to be using, sometimes you see no change, or you even see a little bit of shrinkage. So I ask you, what does that tell you there? So what that would tell me is that there's something in your water, and it may be salts, it may be the treatment of the water that is acting as a kind of a dehydrating agent. So it's causing, the osmosis is always occurring, but it ends up acting like the hypertonic solution. It probably doesn't lose weight as dramatically, or the length as dramatically over time, because it's mostly still water, so you still have water moving into the cell. But if you get some moving out, it may tell you, and sometimes you can taste that your water has kind of a strong taste. There may be some ions in there, salts. Again, it could be minerals that are in there. It could be the treatment, the chlorination in there can actually pull water out a little bit. So something to think about when you're drinking that. So. Okay, so then how do we relate that back to some of the other activities? So let's go back up to activity C. So I'm getting away from percent change a little bit. That's okay. We're tying it all in. You don't have to calculate percent change in activity C, but you should see that kind of pattern there where you see that shriveling. And again, we can't, like I mentioned, we can't measure our blood cells at the cell level. We could, but we don't typically do that. But you should see that kind of shrinking that goes on there. If it's in kind of a balanced solution, which we're always hoping for, but usually our bodies are not exposed to, water's moving in, water's moving out at about the same rate. Keep in mind with osmosis, water's always moving in and out of the cell. It's just, is more moving in or more moving out, or is it about the same? So in the first slide, you see an example of where water's moving in and out at about the same rate. The blood cells are nice and hydrated. They don't have too much water or too little water. In situations, and again, we do this to our bodies all the time, where you have cells moving in and out or water moving in and out, but you have a lot more moving out because you drank, it's a pumpkin spice latte or something. So it's got a lot of sugar and it's got a lot of caffeine. You will feel dehydrated from that. And so again, we all kind of, that I'm thinking about it, respond by drinking a lot of water. So alcohol will do the same thing. Sodas will do the same thing. They have salts and sugars and caffeine, so sometimes that can really dehydrate you. And so sometimes people keep reaching for more sodas and it becomes a vicious cycle there. So, and then in the last example is if water is moving into the cell at a really high rate, and that's only going to happen if you're drinking a lot of what's called pure distilled water. So you actually don't want to ever drink in the lab. We have the super purified water that actually would be lethal to you if you drank that all the time, because it has so few solutes. It's actually less concentrated than the inside of your cells. So water ends up in those cases moving into the cells at such a fast rate. So in that first slide, again, we've got about a even rate in and out. In the second slide, in the salty/sugary solution, then we've got the rate is moving out of the cell overall. And then in the last one, I don't know why my ink's disappearing here, but in the last one, you have water moving into the cell at a really high rate. Again, a little bit moves out, but not that much. So as it moves into the cell ends up rupturing. It's very hard to replicate that. There are some occasions where people overhydrate, they drink way too much water, and you're at this point really ignoring your body signals, because we all know what it feels like to drink too much water. You get that waterlogged feeling. So if you're drinking way too much water, your blood cells can rupture, and of course that's probably going to put you in a pretty bad situation, because when your red blood cells rupture, you're no longer carrying oxygen throughout your body. So occasionally you hear about medical mistakes too, where they don't get the IV concentration right, and so the outside of the cell is really, really low in concentration. And I think this is going to disappear again for some reason. And so this water ends up flooding the red blood cells, and this could be a patient in critical shape anyway, and then their cells end up rupturing. So, okay, that's all I have for this. I hope that this has been helpful for you. Please contact me with further questions.